Hello students, this session is for Engineering Chemistry, the course code CYT 100 for S2 Beta K2 students. And I am Dr. Deepa K. Baby from the Department of Basic Science and Humanities, Rajagiri School of Engineering and Technology. The current session, Instrumental Methods and Nanomaterials, consists of mainly three parts. The first part deals with thermal analysis, and in this we are studying thermogravimetric analysis and differential thermal analysis. The second part is chromatographic techniques, and third part is classification and preparation of nanomaterials. The first session we are dealing with thermal analysis. Thermal analysis involves the measurement of physical and chemical properties of a substance, and it is measured against function of temperature. The physical and chemical reactions taking place in a sample involves the following reactions, that is vaporization, dehydration, crystallization, decomposition, dissociation, combination, oxidation and reduction reactions. In thermal analysis, we are plotting these reactions against function of temperature. And first we are dealing with thermal gravimetric analysis. In thermogravimetric analysis, first we can see what is the principle behind it. It is a technique in which mass of the substance is plotted against temperature. Mass versus temperature. For this, we are heating the sample in a controlled heating rate, that is from room temperature to higher temperature as high as 1200 degrees Celsius in a controlled heating rate. The graph obtained from this instrument is known as thermogram. Thermogram is a plot of mass against temperature. Or you can plot differential thermogram. In this, we are plotting difference in mass divided by difference in temperature against temperature. You can study a sample qualitatively and quantitatively from this instrument. Next comes the instrumentation part of thermogravimetric analysis. Mainly, it consists of a power source. To heat up the furnace, you need a power source. Next, you need a furnace, and the furnace is provided with atmosphere control, or it is known as environment control equipment. It is nothing but you have to fill nitrogen or helium gas to provide inert atmosphere inside the furnace. For this, you are using environment control equipment. Then you need a sample holder where you can place the sample. Normally, you are taking 5 to 20 milligram of sample in the sample holder. Then you need a temperature sensor to record the temperature of the sample. Then finally, you are passing the signal to recorder, and the recorder will plot the mass versus temperature graph. Then next is how this is working. First, we are placing the sample 5 to 20 milligram in the sample holder using a silica crucible. Then using power source, you are heating the furnace, and the reaction will take place inside the sample, and this reaction will lead to mass loss, and the mass loss is recorded by an analytical balance. Analytical balance again records the mass change, and temperature is recorded by temperature sensor. Recorder will plot the mass versus temperature graph. This is the thermogram obtained from thermogravimetric analysis. You can see it consists of two regions. First region is the horizontal region. That region indicates the thermal stability of the sample, and this region is known as plateau region. The second region, where you can see a decrease in mass, and this region is said to be inflection region, and physical and chemical reaction takes place in this region. As a result, mass loss occur, and this mass loss is measured by analytical balance. Here mass is plotted against temperature, and the graph is known as thermogram. Then what are the interpretations from this? You are having two portions. One is horizontal portion, other one is slanting downward portion. Slanting downward portion is the region where reaction takes place, and horizontal portion is the region where it shows the thermal stability. Then what are the applications of TGA? TGA is mainly have many applications. First, it is qualitative applications are there. Quantitative applications are there. You can study a polymer using this TGA. Then purity of a sample can be measured. If there is impurity in the sample, then there will be a depression in the melting point. Then distinguish different mineral compositions using this TGA. The qualitative analysis can be studied by taking an example, that is calcium oxalate monohydrate. First, the calcium oxalate monohydrate is heated in a furnace. Up to 100 degrees Celsius, you can see there is no change in mass. That means the compound is thermally stable. After 100 degrees Celsius, you can see a sudden decrease in mass. And this is due to the reaction, dehydration reaction, and the product obtained is anhydrous form of calcium oxalate, and that is CaC2O4. Then CaC2O4 undergo decomposition reaction near 346 degrees Celsius, and you are getting calcium carbonate. Finally, calcium carbonate above 600 degrees Celsius undergo decomposition to give CaO. And this is the stable form, and this decomposition takes place beyond a temperature 600. Next is differential thermal analysis. From the name itself, differential thermal analysis, difference in temperature is plotted against temperature. That is, you need a sample and inert reference compound. The inert reference compound means it is thermally inert at a higher temperature. Using these two, that is sample and inert reference, you can measure the temperature change, and the temperature change occurs by some reactions, and the reactions are classified as endothermic reaction and exothermic reactions. These two reactions are plotted against temperature. That is differential thermal analysis. The plot obtained from differential thermal analysis is known as differential thermogram. Again, come to the instrumentation part of DTA. Again, it consists a power source to heat up the furnace. And this is the furnace, and in this you can see two holders, one to place the sample, another one to place the reference, that is the substance which is having high thermal stability, or the substance which does not undergo any chemical or physical reaction when it is heated up to a higher temperature. For example, you can take alumina or silica as a reference material for this DTA. Then it is thermally insulated, and it is provided with environment control equipment. Environment control equipment is a gas cylinder through which you are passing inert gases like nitrogen or helium into the furnace to make an inert atmosphere inside the furnace. Then you have to measure the temperature of both sample and reference. For measuring sample temperature, you need a thermosensor, and it is marked as thermosensor 1. For measuring the reference, you are taking temperature sensor 2. Then both are amplified and it is recorded, and the recorded plot the graph, that is delta T versus temperature. And the working of DTA is that first you have to place a sample which is having a composition 5 to 20 milligram. Next, you need an inert material. Material mainly used is alumina, and it is placed in sample holder and reference holder. Then both are heated at a controlled heating rate from room temperature to higher temperature. Then difference in temperature of the sample and reference is taken as delta T, and this delta T is plotted as a function of temperature. And the graph obtained from differential thermal analysis is known as differential thermogram. It consists of two types of peaks. One is an upward peak, that is above zero value, and one is an endo peak, that is below zero value. It is also called downward peak. And if there is no reaction, then you will get a line passing through zero value. What does it mean, this exothermic peak and endothermic peak? Exothermic peak is due to reactions such as adsorption, crystallization, oxidation, polymerization, which liberates heat. Endothermic peak is due to endothermic reactions like desorption, absorption, sublimation, fusion, etc. and that needs heat to carry out the reaction, and that is termed as endothermic reaction. The next is applications of DTA. The main applications of DTA are you can study the thermal behavior of inorganic substances such as clay, cement, etc. Next, you can study the phase transitions of a compound. For example, you can take sulfur. Sulfur can exist in different crystalline structures, that is monoclinic, rhombic, etc. You can study the phase transition from rhombic to monoclinic using this DTA. Next, you can study the melting and boiling point of a substance. Transition temperature can be monitored. Then quality control of cement, glass, etc. can be studied using DTA. Then qualitative analysis, again you can take the example calcium oxalate monohydrate. The main reactions undergoing by calcium oxalate monohydrate are dehydration, oxidation and decomposition. Dehydration reaction is an endothermic reaction, therefore you are getting a peak downward. Then oxidation reaction is an exothermic peak, therefore you are getting a peak in upward direction, and the product is CaCO3. Then third, you can get again an endothermic peak, and that is the decomposition of CaCO3 to form CO2. And this is the thermal behavior of calcium oxalate when it is heated from room temperature to high temperature, that is up to 1200 degrees Celsius.